In the previous section, we talked about current. And current, we know, is the change in charge over time, or the movement of charge over time. So we can also visualize it as electrons moving through a wire, because that is the same thing as current. And we know that current moves in the opposite direction of electrons because current is the flow of positive charges, and electrons have negative charge. So, in the previous example, we talked about Ohm's law, which is voltage equals current times resistance. And in this, we thought that current was constant. Current didn't change. And that is DC, or direct current. But often, current is changing. It changes with time. And we call that AC, or alternating current. So, let's plot alternating current. On the y-axis, we have current, which we give unit of I. And current, which we say is I, has units of amps, which is A. And we have time on the x-axis. So over time, the current changes. So, what is the equation for this? We have I, current, equals I naught, which is peak current, which is the amplitude of this right here, I naught, times sine, because it's a sinusoidal function, times 2 pi frequency over time. So, why do we say 2 pi times frequency? Frequency, we know, has units of hertz, which is 1 over a second. So frequency represents the number of cycles per second. From pre-calculus, you know that multiplying 2 pi times frequency gives you radians. And to use this equation to plug into sine, we need radians. So we could say that this equation instead was I naught sine of omega t, omega being radians of the frequency. Radians per second. Now, we know Ohm's law, voltage equals current times resistance. So let's change Ohm's law, and we'll make it current equals voltage over resistance. So let's rewrite this equation with voltage, because voltage also changes as a function of time. So voltage equals peak voltage, which is the amplitude, times sine omega t. In the last section, we wrote it this way. Voltage, resistance with current going this way. But now, we can do it this way. This represents alternating current. Now, when we talk about alternating current, there are a few things we just need to memorize. If we have an equation sheet on our test, we just need to write them down so we know. The first is I, RMS. And this is current root mean squared. In a solve for current root mean squared, we take the peak current, which is the amplitude of this function, or the maximum current at any time, divided by the square root of 2. Voltage RMS is equal to peak voltage divided by square root of 2. And average power, which is P with a bar over top of it. The bar over top of it represents average, is equal to I RMS times V RMS. We talked about power in the last section. So please memorize those. So let's say we have a wire. And we have a current going through this wire. And it has surface area A. A is area. So, we're going to introduce a new equation, and that is for current density. And current density has units of J. That's the unit we give it. And it is equal to current divided by area. So when we solve for it, we're going to have units of amps per meter squared. J is the variable that we use to call current density. So solve for area, that's easy. It's probably pi r squared. You know current, easy to solve for current density. Now there's something else we should talk about, and that is drift velocity. So, we talked about current. Current is the change or the movement of a charge over a certain amount of time. So you may think, okay, current is the speed that electrons flow in the wire. This isn't true. So we have our wire right here, has a certain area, has a certain length, and we put a current through it. When electrons travel through a wire, the electrons hit all these different atoms and they go everywhere. It's not the speed of light going through. It's actually pretty slow. So we have an electron here, goes here, collision, here, collision, here, collision, here, collision, 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 and finally gets out of the wire. So all these collisions that are happening because of atoms slow down the electrons. And trying to figure out the electron speed is this. It is drift velocity. Drift velocity, units of VD, is the speed that electrons move through a wire on average. Now I'm going to teach you how to calculate what drift velocity is. Okay, we have current equals to negative N E A over drift velocity. I is current. N is equal to the number of electrons per meter cubed in the material. So what are the number of electrons per the volume? E is the charge of an electron. We know that this is equal to negative 1.602 times 10 to the negative 19 coulomb. A is equal to the cross-sectional area of the wire, which is like this right here. It's the area. And VD is the drift velocity. That's the average speed that electrons move through the wire. So, if you know all these constants except one, you can solve for the final constant. So if you know current, you know the density of the material, the molar mass, that kind of stuff, you can solve for electrons per meter cubed. E is a constant. A, you know pi r squared, solve for that, and you can get drift velocity. Another way to solve this equation, you notice you can move this A over here, so I over A. We know that that is equal to current density, which is J. And that equals negative N E times drift velocity. N, electrons per meter cubed. E, negative 1.602 times 10 to the negative 19 coulombs. And VD is drift velocity. Using these equations, you'll get a problem, you'll know everything in the question except one constant. You plug everything in, you solve for that constant.